The last topic we are going to cover in this course, in this very short course, is a brief description of a very important subject, namely that of thermodynamics. Now, we began this course by understanding a little bit about the mechanics and dynamics of individual particles, single particles, two particles, or a collection of particles, and so on. We went on to understand what happens when you have a wave motion, when you have waves in a continuous medium such as a string or air or a solid medium, and then we also studied a little bit about the dynamics of fluids, namely what the equation of motion of a fluid is, what its consequences are, and so on. So, logically the next thing to do is to ask what happens when you have a very large number of collection of particles, and this is what matter generally is, because we know that matter consists of atoms and molecules, and we know that the number of these molecules or atoms in any normal size sample of matter is exceedingly large, astronomically large. In fact, it is bigger than astronomically large, because it is of the order of Avogadro's number typically, which is of the order of 10 to the 23 or 10 to the 24. So, we are faced with this problem that we need to be able to understand the collective behavior of an exceedingly large number of elementary constituents, whether they are atoms or molecules does not matter, but we need to be able to come to grips with this problem of describing systems with a very large number of elementary constituents, or a very large number of degrees of freedom in technical terms. This requires totally different techniques from the ones that we have been talking about so far, and thermodynamics is one such technique. In fact, the subject itself, and I am going to say a large number of things in words today, I am going to do a lot of talking because it is a deep subject, it has very profound subtleties in it, and it is good that we understand what is involved in this subject very clearly before we begin to understand or carry out the mathematics involved in the subject. I want to make a special point of this today, because the general impression that the beginning student gets from courses, elementary courses on thermodynamics or statistical mechanics, is that it has to do with a lot of partial differentiation, partial derivatives, using the calculus in various ways and so on, without much physical content. Nothing could be further from the truth. This subject is an extremely physical one, it is based on physical postulates, it describes real physical systems, and is in some sense a very fundamental subject, if I may say so. There are several definitions of thermodynamics possible. The one that seems most suitable here would be to say that it is in fact the study of the transfer of energy from one system to another, if you like, or the energetics of systems, and as you know, energy is one of the most fundamental physical quantities with which we are preoccupied most of the time. So, in that sense it becomes crucial to understand how to deal with systems with a very large number of degrees of freedom. Most of what I am going to say today will be qualitative, will be statements that I make, and I will try to the extent possible to write them down on the board, even at the expense of being very slow as I go along in terms of coverage of material, because I think the issues involved are so deep and so subtle that it is good to spend time and understand them clearly right from the beginning. Throughout, I am also going to be pointing out that thermodynamics itself is not a fundamental subject in that sense. It is derived from a deeper subject called equilibrium statistical mechanics, which is outside the purview of this course, but which is needed in order to understand the laws of thermodynamics. And let me say it right out in the beginning, the laws of thermodynamics, a very small set of laws, tell you a huge amount of information about systems, large systems, but the laws themselves are not really fundamental laws. These laws are derivable from a more from deeper considerations, from what is called the fundamental postulate of equilibrium statistical mechanics. We probably will not get to that in this course except in passing mention, but it is good to remember that thermodynamics is a derived subject in a very, very specific and precise manner, which I will explain. So, our first problem is to ask what happens if you took a container of some specified volume V and you put n particles in it, where this n is very large, so much greater than 1, say of the order of 10 to the 24 or something like that, and you have these particles moving about in this container, if it is a container of gas, interacting with each other, and we would like to know what physical information we can get from this system, how to understand the physics of this system of particles which are interacting with each other. You can see immediately, based on our experience in mechanics, we wrote down the equations of motion for one particle or two particles in the central force problem. Even that was formidable and quite difficult to solve, and I pointed out that when you have 3 or more particles, you really do not have enough constants of the motion to solve, quote unquote, the problem analytically in closed form. So when you have 10 to the 24 particles, it is completely hopeless to do this, but still in principle we could ask, what is it that we need in order to understand the physics or the dynamics of this set of particles? What you would need is, of course, the coordinates of all these particles, where I labels the particles 1 to n, if you like. You would need to know their momenta, pi. You would need to know the forces on all these particles due to every pair. So you would need to know what is the force, net force on the particle I, F sub I, and what is its angular momentum, and what is its energy, and so on and so forth. You would need to know all these dynamical variables at any given instant of time, and then in principle you would solve Newton's equations of motion for each particle and write down the solutions for all the dynamical variables at any subsequent instant of time. Now this is obviously impractical if you have 10 to the 24 particles. Not only is it impractical, it is virtually impossible. Not only is it virtually impossible, it is actually useless in some sense, because at the end of the day, when you look at a system like this, the questions we ask of this system do not require a detailed knowledge of these quantities here. The questions we would ask, for instance, if this is a gas, would be, how much should I heat this gas in order to make it do a certain amount of work? What is the energy input that I can give to this gas in order to extract some work? How much heat comes out of this gas when I do some work on it, and so on. So these are questions which have nothing to do with individual particles at all. They are clearly questions which have to do with on a much larger coarse grained scale. For instance, if I want to know what is the pressure of this gas, what I would do is to ask what is the force per unit area on the walls of this gas on the average. I do not worry about what happens every picosecond, because the particles interact, they hit the walls, etc., and the action is actually happening in picoseconds or less. That is not what I am measuring. What I am measuring is over a larger time scale. I am measuring some kind of average force here. So the key word here is average. I am always averaging over all the possibilities of what the elementary constituents can do. So this is the whole point, that the knowledge of these variables, which I should call microscopic variables. I am going to use this term microscopic in a very specific sense. By microscopic I mean the variables pertaining to each individual elementary constituent of this system, namely each molecule or each atom of this system. Those are the so called microscopic variables, and if I do this for all the variables, a specification of all these tells me everything in principle that I need to know about the system at any given instant of time, and I would call that a microstate. Of the system. A microstate involves knowing this for the full set of particles. So dot 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 for I equal to 1, 2 all the way up to n. So a microstate involves a great deal of information. It involves knowing completely the state of each elementary constituent of the system at any given instant of time, and obviously for a system like this the number of microstates is enormous. For instance, even if each particle, instead of a particle, imagine replacing it with a coin or something like that. A coin has only 2 states, there is a head and there is a tail. So if you have n coins, the number of possible head and tail combinations that you can form from the set of n coins is 2 to the power n. It is already exponentially large in the number of particles n, and that is what happens in a real system. The number of possible microstates is truly astronomically large. It is exponentially large in the number n here. that is important to remember here. So, even listing all these states can be quite a formidable task in general, but in principle we can think of doing so, and we know that there are large numbers of microstates of the system. On the other hand, I already said that the kind of questions we ask of such a system would be average questions. There would be questions about what is the average total energy of the system. So, let us write down some of these variables. Average total energy. What is the volume of the system? What is the number of particles in the system, the total number of particles here. And then we could ask more detailed questions like what is the pressure of the system, what is the temperature, and so on. We have to define these quantities yet, but we have a whole lot of these things here. We also know that if it is a thing like a gas or a liquid or something like that, there would be a lot of disorder, and we have to specify what is meant by this disorder. We must have a quantitative measure of this disorder, and that is called the entropy of the system. I will write a symbol down for it and explain what it is a little later. So, there is this symbol, and so on. So, we have a whole collection of these variables which are in principle related to these microscopic variables, but in practice would be some kind of averages over various possibilities for these microscopic variables here. And what would one call these? I would call them macroscopic variables, and a specification of these would be specifying a macro state of the system. And the statement I am making now is that in thermodynamics and in general for such systems, we are interested in the macro states of the system. We are trying to find out here what certain average properties are like for the system, and then extract as much information as possible from it. And what thermodynamics does is to study these average quantities. If you like, these are thermodynamic variables. This set of variables are thermodynamic There are several other thermodynamic variables, we will talk about a few of them, but you should appreciate right away the distinction between these microscopic variables pertaining, there is nothing to do with a microscope, the word is used only in the sense that these are the variables corresponding to the very small constituents, individual constituents of our system, and these variables are the micro states are specified by specifying all these microscopic variables, whereas the thermodynamic state of the system is specified by specifying the macroscopic variables, the thermodynamic variables. Okay. Next point, the whole science of thermodynamics, the word is a misnomer unfortunately. It should have been called thermostatics, because there is no time dependence in thermodynamics, not at this level in any case. Thermodynamics deals with systems in thermodynamic equilibrium, and let me, so important a definition that we need to write it down. So, thermodynamic called thermal equilibrium there is a technical way of defining what thermal equilibrium is, but unlike mechanical equilibrium where we understand, for instance, if you have a particle in a harmonic oscillator potential, the equilibrium point is the minimum of this potential. Similarly, we can talk about a thermodynamic equilibrium. This would be a state which corresponds to these thermodynamic variables being at some minimum, sometimes maximum depending on how you define it, a minimum of some thermodynamic potential, if you like, which has not got the connotation of potential energy, but it can be cast in a language which looks like this, which looks like the minimum of some energy. But the better way to define thermal equilibrium is to say that it is a state in which of a system, a macroscopic system, in which these averages, these thermodynamic variables have values which are time independent. So, there is no time dependence at all. All macroscopic average values are time independent. As I said, this can be made more rigorous, but for our purposes this suffices at the moment. This definition is enough. Macroscopic average values. Now, of course, this means that if you go back to this analogy of a gas here, this means we are thinking of a situation where the system is static, the macroscopic system, in the sense that the pressure of this gas, which is the average force exerted per unit area of the walls of the container, is independent of time. It does not change with time at all. Of course, dynamics is going on inside, things are time dependent because the molecules themselves are flying about, colliding with each other and so on, and there is a lot of dynamics going on. The system is not in mechanical equilibrium in that sense. The elementary constituents need not be in equilibrium at all, of course they are moving, but the averages of the macroscopic quantities are time independent. And of course, should you want to change the state of the system, you must do so in such a way that thermodynamics continues to apply, which means you always do it sufficiently slowly that the system attains thermodynamic equilibrium always. For instance, a very famous example would be to take a piston, a gas, and put a piston over it and move the piston out very slowly, and there is a gas here. So, what you are causing is an expansion of this gas here, but it is done so slowly that at any instant of time compared to the time scales on which the molecules move, the system is essentially static, that the average quantities are time independent, and this is called quasi static thermal equilibrium if you like. So, the processes are slow enough that you do not have any sudden time dependence coming in. One can extend this and consider cases where there is time dependence, but in the most elementary definition I am talking about here, there is no time dependence of these quantities. So, the word itself, thermodynamics, should have been something like thermostatics, but we are stuck with this term here, so we will leave it as it stands. Okay. So, now we made some statements so far that we are going to look at cases where you have a large number of elementary constituents. We will not worry about the detailed dynamics of what happens to these constituents, but we will look at average quantities which are averaged over all possible various possible configurations of the elementary constituents themselves, okay, and that should give us some information. The real miracle, the incredible thing is that even though we are sacrificing detailed information about the microscopic constituents, we can still, using just a very small number of laws, namely the laws of thermodynamics, extract a great deal of information about these average quantities that we are interested in. So, that is the real miracle of thermodynamics here. In the same breath, I should also say that the system itself, I have been talking about average quantities such as the average energy and so on. What do I mean by that? Well, if I take a beaker of water and put it here on this table in contact with the rest of the atmosphere, then as you know, if the water is very hot, it is hotter than the atmosphere, it loses heat to the atmosphere gains a certain amount of heat, and the whole thing equilibrates at some common temperature. This water is then in thermal equilibrium with the rest of the system, which I would call a heat bath or a reservoir, the atmosphere around it. Now, the molecules of this object are moving around, but the fact that it is at a fixed temperature is a reflection of the fact that the average kinetic energy of each molecule is fixed. it remains unchanged in time at some value which is determined by the temperature. In fact, the temperature is a measure of this average kinetic energy. But what is interesting is that all the time there are molecules flying out of it and getting back into it. There are things going into the vapor above the liquid and molecules getting back into the fluid here. There is a lot of agitation, thermal agitation here. So the actual total energy of the molecules of this fluid is not fixed, it is fluctuating. It fluctuates extremely rapidly with time. So that is the whole point, that an object like this does not have, if it is in contact with the atmosphere, does not have a fixed energy. A system at a constant temperature does not have a fixed energy. On the other hand, it has a very definite average energy, and the symbol E that I have used here is for the average energy, average over all the fluctuations which arise due to the random thermal motion of the molecules here and of the atmosphere. Now this realization of what is meant by thermal noise took a long time to occur. It is at the root of what we mean by heat itself. So let me write that down. Heat itself, the energy of random molecular or atomic motion at the atomic or molecular level, the so called random molecular motion. It is not random in principle. In principle, if you actually know all the forces, all the momenta of all the particles, all the positions and so on, then in principle one can compute what these quantities are at later instance of time in principle, and then there would be no randomness. But in practice, of course, there is randomness because we do not have that detailed information. So this random molecular motion, the energy of corresponding to that is what we call heat. It took a long time for this recognition to sink in. It came in the 19th century once people like Boltzmann and Gibbs and Maxwell and so on elucidated what is meant by thermodynamics and statistical mechanics, and then it was realized that the fluctuations that arise due to random molecular motion is very crucial. These fluctuations are important, and thermodynamics is a science which averages over these fluctuations and deals with these average quantities alone. So in that sense, thermodynamics is the science of averages of macroscopic quantities. It is not that the fluctuations are unimportant, they are important, but there is no way of calculating them in general inside the purview, in the purview of thermodynamics itself. You need to go to a more fundamental subject, namely equilibrium statistical mechanics, in order to find out what the effect of the fluctuations is. I will say a little more about this as we go along, because it is important to understand the origin of things like specific heat. Okay. Now having said this about thermodynamics, let us immediately ask, what sort of variables are we dealing with now? What are thermodynamic variables really? We have listed a few there, but is there a better way of writing these variables? Well, since we are going to deal with large systems, it is clear that all these variables can be quite large in numerical value. Avogadro's number itself is much larger compared to unity, and it turns out that you have two kinds of thermodynamic variables. Of two kinds. One is the extensive variety and the other is the intensive variables. What I mean by extensive variables are those which depend on the system size. In other words, if the system size or the number of particles n that is the foremost example of an extensive variable, practically defines what I mean by an extensive variable, the volume of the system. These are extensive variables, they increase with the size of the system in some loose manner. On the other hand, corresponding to these two objects, one can think of an intensive variable which does not depend on the actual physical size of the system. For instance, the number of particles per unit volume. So, number density N over V. This clearly does not depend on the size of the system. If I take a certain volume and put volume V and put n particles in it, I double V, I double n, the density does not change. So, it is an intensive variable here. And more similarly, whether it is the mass density or number density does not matter. If I have several species of chemical molecular species there, then the concentrations of various species is certainly an intensive variable here. The temperature is an intensive variable. In fact, the temperature is related, as I pointed out, to, and we will come back to this, to the average kinetic energy of each molecule. So, it is actually dependent on individual molecules, the property of individual molecules, which means you would take the total energy, divide by the total number of molecules, and you would get something like the temperature effectively. So, this again is an intensive quantity here. The pressure is an intensive quantity. Why do I say this is an intensive quantity? This is the average force per unit area exerted, for example, in a fluid or a gas, but what would that in turn depend on? This pressure would again be force averaged over a large number of particles, and you can finally reduce it to a quantity which is dependent on the density and the temperature. Anytime you write an equation of state, you are really saying what the pressure is in terms of other intensive quantities. And in case you are not convinced by this, let me point out, you already know this, we are going to do this again. Remember, the ideal gas equation of state was PV was equal to N times RT. This is the form in which you are used to the law. Let us not call this N, I will not use just N. N is the number of moles, that is what you are used to. This equation can be rewritten as PV equal to the number of particles times Boltzmann's constant times T. So, there is N, and you can rewrite this as P is N over V K Boltzmann T, and this quantity is an intensive variable. This is an intensive variable, therefore, this is an intensive variable as well. The pressure is definitely an intensive variable. Can we think of anything else here? Well, certainly the average energy of the system. So, I will use the symbol E, although it will turn out that very often for a specific kind of energy you use U here for the internal energy. I will talk about what this U is a little while later. Similarly, a measure of the disorder of the system, the so called entropy of the system, and so on. These are all extensive variables. If you increase the system size, these quantities also increase in proportion. On the other hand, these quantities do not, and they form intensive variables. Now, clearly when you have an equation between two quantities on the left and right, the left cannot be an extensive variable and the right can't be an intensive variable. They must be of the same kind as we see here. Sometimes you may want to write things in terms of extensive and intensive quantities, but then the fact is that buried in here in NR is this number here, and therefore that is an extensive quantity, this is an extensive quantity, and this way of writing it tells you it is a relation between two intensive quantities. If you bring the mass density into the picture, this is rho K Boltzmann T divided by the mass of a molecule. That is the mass density which is intensive, that is intensive, and this is intensive.